Let's get started. Welcome to the IEMS seminar. I will mention that this seminar is being recorded. So today we're pleased to welcome Jeff Hong. Jeff received his PhD in Industrial Engineering and Management Sciences from us back in 2004. He's currently the Fudan Distinguished Professor, the Hong Yi Chair Professor, and Associate Dean of the School of Data Science at Fudan University in Shanghai. He's also the Simulation Area Editor of Operations Research and President of the Informed Simulation Society. Now, Jeff, I think the chain from Bruce Smizer to me to you has got to be the longest advisor to student chain holding both of those positions that's ever existed.
Oh, really? Wow.
Of all of my students, Jeff was the fastest from idea to proofs to finished paper by a long shot. In fact, I had to write a letter to appeal to the graduate school to allow him to do his prospectus and his final oral in the same year. Now, Jeff's very creative. I remember one day he walked into my office and asked if I had ever heard of Voronoi diagrams, which I hadn't, because he had a radical idea for a new locally convergent discrete decision variable simulation optimization algorithm based on them. In a few weeks, that idea became Compass, which is now one of the most highly cited algorithms in the field. It's been a real joy to watch his career. Today, Jeff is going to talk about large-scale ranking and selection in parallel computing environments.
Okay, I will start. Thank you very much for this very nice introduction. I actually started my PhD study at IEMS department exactly 20 years ago. So time flies. So it's just look back, it seems like yesterday, but it's already 20 years. I feel really good to be back today to talk about my research. So today I'm going to talk about large-scale ranking and selection in parallel computing environments. It's a joint work with my former PhD student, Dr. Yin Zhong, so also here today. So in case I have some question I couldn't answer, so I have him to back me up. So this is an outline of today's talk. I'm going to give a very brief introduction to ranking and selection. Then I'm going to talk about this procedure we have developed called the lockout tournament procedure. I'm going to show you some numerical study. And in the end, I will talk about the extension of this lockout tournament procedure to fix the budget ranking and selection problem. So the last part is our current work. I'm going to show you some of our preliminary results. So first, let's look at the ranking and selection. So the problem itself is quite simple. Say if I have k alternatives, and so you can think about these k alternatives are k normal random variables with unknown means, and sometimes also with unknown variances. So the ranking selection studies how to develop a statistical procedures that can identify which alternative has the highest by only running simulation experiments. So typically we want this to achieve a certain statistical guarantee. So that's why this type of procedure is also called the fixed precision ranking selection procedures. If you look at the ranking selection problems, it's a type of simulation optimization problems, and it's used in practice to select the best design or best strategy, best policy, from a number of alternatives. So the simulation is very useful in evaluating different alternatives and different scenarios. And our goal is often to find the best design. So the ranking selection fit into that framework. So in this talk, without a loss of generality, we're going to assume that alternative K is the best and alternative Y is worst. We have this rank here. And so therefore, our goal is to identify which alternative is K. So because of the best alternative and the second best alternative, let's say, they can be arbitrarily close. So if they are arbitrarily close, it becomes very difficult to tell which one is better. Therefore, you probably need an infinite amount of sample to tell that. So to address that issue, so Beckhofer this 1954 paper proposed this indifferent zone formulation. Basically, they want a procedure to guarantee to identify the best alternative with the probability at least 1 minus alpha, given that the difference between the best and the second best is at least a delta. So this delta is called indifferent zone parameter. It is typically interpreted as the smallest difference that the experimenter feels is worth detecting. And in this paper, we're going to stick to this classical indifferent zone formulation. But I do want to note that Barry and I, and also my former PhD student, Fudan, we had a paper showing that basically it's possible to design different zone indifferent zone procedures. But in this talk, we're still going to consider the indifferent zone formulation. And if you look at the ranking selection procedures, in general, there are two different types of ideas. One is a stage-wise procedure, the other is sequential procedures. Stage-wise procedure, basically, you can think about is trying to determine the sample size of all alternatives at once. Then we're going to go collect all the samples of all alternatives at once. And we're going to select the alternative with the largest sample as the best. And sometimes, because the variance is unknown, so we probably need an initial stage to estimate the variance. Then we're going to determine the sample size and collect all the sample size. So those are the stage-wise procedures. Another type of idea called the sequential procedures. The basic idea here is we're going to determine the elimination criteria. Then we're going to collect sample sequentially, sometimes one at a time, for all surviving alternatives. So once we collect a new round of sample, then we're going to check whether the elimination criteria are satisfied. If they are satisfied, then some of those alternatives will be eliminated. Right. So we're going to do this until only one alternative is left. So those are the sequential procedures. So I'm going to give you two classical examples about these procedures. First one is a stage-wise procedure. We look at the earliest work, so the Beckhofer's procedure in 1954. So basically assume that all the variances are equal and unknown. So then it goes on to determine the number of alternatives, to determine the sample size for all alternatives. So in this way, we have n equal to this one here. So it is inverse proportional to the square of the indifferent zone parameter and proportional to variance. Very easy to understand. And it also has a parameter which is called h in it. So h depends on alpha. That's the probability of incorrect selection. And it also depends on the number of alternatives k. So then once you determine the sample size, then you go collect this amount of samples for all alternatives. Then you're going to pick up the alternative with the largest sample mean as the best. So the basic idea is what would be considered as the best? Well, it is the one that is better than all others. Right, so then Beckhofer basically showed that by properly choosing this constant h, you can prove this probability statement. This probability statement basically said that, because we always pick up the alternative with the highest sample. So in order for us to make a correct choice, so we want the sample mean of the best alternative is better than all others. So in that case, we're going to select alternative K, which would consider a correct choice. So we want to choose the constant H so that this probability is greater or equal to 1 minus alpha. And from this probability statement here, we can see if K become higher, because we're talking about large scale problems in this talk. If K increases, then to guarantee this probability statement become more and more difficult. So therefore, we can see that typically the sample size n will increase in K. The small n will increase in K, because this is essentially saying that we want this to be higher than this maximum. When K become higher, then the maximum will become higher. So the sample size small n typically increase in n. Then if we look at the total sample size, capital N, that's small n times k. So we'll increase typically faster than k. And I want to emphasize that again, what we would consider to be the best is that your sample mean is better than all others. This seems quite straightforward. I mean, if you think about what is the best is the one which is better than all others. But however, later on we'll show you that our idea actually deviated from here. And this is a back office classical procedure, and there are many extensions to handle unknown and unequal variance, and sometimes they also allow the use of common random numbers. So I have a very quick introduction of common random numbers. We know that in the computer simulation experiments, to generate the output, you usually use a sequence of random numbers. So therefore, common random numbers is a technique that uses the same random number to generate observations from different alternatives. So to introduce this positive correlation among them. The reason we want to introduce positive correlation is because when we compare them, we essentially look at the difference here. So when you have a positive correlation in that, then the variance of this difference will become smaller. So the comparison will become sharper, and the same sample size will become smaller. But one problem to use common random numbers in large-scale problems, parallel computing environment, is that you have to coordinate. You have to coordinate all alternatives and all observations to use the same sequence of random numbers. Sometimes that can be quite challenging to do. So those are the about the stage-wise. Next, let's look at one example of a sequential procedure. We look at another classical procedure, the Paulson's procedure of 1964. Again, we assume that all the variances are known. And the basic idea here is that we're going to construct this triangular continuation region here. So this continuation region is determined by two parameters. One is the slope, lambda. So lambda we usually choose between 0 and delta. Delta is the indifference parameter. And another important parameter is this A, which is the intercept. And A is defined in this way. So once we define this triangular continuation region, then we collect sample one at a time from all surviving alternatives. Let's say at stage T, so we have already collected T samples, and alternative I and alternative K are still surviving. So we look at their difference. That will be ZIKT. So as T move from 1, 2, 3, 4, and go on, so essentially you define a stochastic process here. So the basic idea is that if the stochastic process remains inside of the triangular continuation region, we're going to let both alternatives to continue to take more observations. If this ZT goes out of the triangular region from the lower side, then we claim that alternative K is better than alternative I. We're going to select alternative K. Otherwise, if it goes from the top side, then we're going to select alternative I. So you can see from here. So the reason people like people develop sequential procedures is because if the difference between the mean of mu I and the mu k is high, then the slope of this stochastic process will be high. So we'll leave this triangular region earlier. So that means if I know I have enough information, then I don't need to take that many observations. So I can cut the total amount of samples I need. So typically, sequential procedures are more efficient. But to run sequential procedures, you don't just compare alternative I with K because you don't know which one is K. So in the end, you ended up doing all pairwise comparison. You compare each alternative with all other alternatives. So if K is higher, that means when you take one more round of sample, you need to do k times k minus 1 divided by 2 comparison. If you have a million alternatives, that's going to be a huge number. So typically for a small size problem, the comparison time can be ignored. But if your k is very large, then the comparison time can be very large. It can be even the amount of time you spend in comparison can be even larger than simulation. And another thing we can look at here is that you can easily find out the total amount of sample you need to make this decision will grow in the order of k log k. So when the number of alternatives goes up, then per alternative sample size will grow in terms of the order of log k. And for the classical Paulson's procedure, there are also many extensions that handle unknown and unequal variances and the use of common. So those are the two sort of different types of procedures. Now, what do we want to solve? We want to solve a large-scale ranking selection problem. And recent large-scale problems have attracted a lot of attentions. The number of alternatives can be, many thousands or even into millions. And for those type of problems, people typically use a parallel computing environment. And also because of parallel computing environments become very easy to access. And if we look at the two type of ideas we have talked about, stage-wise procedures are very easy to be parallel. So you don't need any coordinations, no communications needed among processes. Very easy to implement, but they are typically not efficient in sample size. Well, sequential procedures are typically efficient in sample size, but however, they require all pairwise comparison. Therefore, you need a lot of coordinations on communications among processes. And also, common random numbers are difficult to apply because you have to coordinate globally, the random number seeds. So what do we want? So in a large-scale problem, so we want an ideal procedure we want should require almost no coordinations and communications, but we also want to be efficient in sampling. So that's the goal. That is a goal for large-scale problems in parallel computing. So next, we're going to introduce this lockout tournament idea we use trying to achieve this goal. But before we talk about the idea, so the first thing we want to establish a result. So we want to establish a result on what is the minimum sample size we need. So especially, when k become higher and higher, let's say k number of alternatives goes to infinity. So what is the lower bound of number of samples? So we have shown that as a lower bound, the sample size has to grow at least in the order of k, so be linearly in k. That's very easy to understand, right? If I have k alternatives, in order to tell which one is the best, at least I need to collect one sample from every one of them. So that will be linear in k. So, however, we have found that in the ranking selection literature, none of the existing procedures can achieve this lower bound. That cast a doubt on this lower bound, whether it's tight or not. It's a lower bound. We don't know if it's a tight or not, whether we'll be able to achieve it. So now let's switch gear to talk about this lockout element. Actually, it's very interesting. I had this idea when I was playing tennis with two of my students. I was having a break watching them playing, and that was in one of the June, in June a number of years ago. So that was during the time of French Open. So I was thinking about this ranking selection problem. So all the procedure we have said. So what would be considered as the best? The best is better than all others. But then I was thinking about French Open. I realized at that year, Rafael Nadal didn't have to beat all other 127 players to win his French Open title. That was his 11th. Now he has already, I think, a 13 French Open title. So he didn't have to beat all 127 players. Instead, he only need to win 7 games. You don't have to be better than all other 127 players. You just have to survive 7 games. So motivated by that, I started to think about, what is special about this lockout tournament arrangement. So in a lockout tournament, suppose you have K equal to 2 to the power of L players. Then, so the winner only need to play L games. So like in the French Open case, you have 128 players, but the winner only need to play 7 games. And what is interesting, the total number of games is K minus 1. And each game need 2 players. So therefore, each player on average play less than 2 games. And what's more, one can actually divide the players into groups. So if I look at this here, so I can say this is first group, second group, third group, fourth group. So literally, you can think about, French Open can have only 4 courts, and I can have all the players in the same group play in their own court. They don't have to talk to, people from different groups don't have to talk to each other. They just play until they have a winner. And then the winner is going to play together. So therefore, if we use that as a comparison to parallel computing environment, so if I assign the player to a processor, they don't even have to talk to each other until they have a winner. And but what is interesting here is each game is a new game. So that means the score you have in the previous round cannot be reused here. So that's something I learned about the lockout tournament, this arrangement. So then it's very easy for us to design a lockout tournament procedure for ranking selection. Again, very similar. We're going to have a game between 2 alternatives at a time. So the winner will go on and the loser is locked out. And when I compare 2 alternatives, I can actually use a sequential procedure here. So that I can use Kane. So guess what Kane stands for? That's Kim and Nelson. Sanke Kim is also a graduate from IEMS department, and we have a Barry. So the Kane procedure is known to be one of the most efficient sequential procedures for in the field of ranking selection. So I can use sequential procedure to compare a pair of alternatives, and so to gain some efficiency in terms of sample size. And I can also group the alternative into groups and process them on different processes. So therefore, no communication and coordinations are necessary among processes until you have a winner. And also, we don't have any pairwise comparison. So because every time we just have two players, so we just need to compare them. So if you look at the number of comparisons, that's actually equal to the half of the total sample. Because you have 2 players, each one of them collect a sample, then you compare them once. Because a single comparison time is much smaller than a single simulation run. So if your comparison number of comparisons is equal to half of the total sample size, then the comparison time can be ignored. And also this procedure can easily handle unknown unequal variance. I just need to use unknown unequal variance version of a K procedure to do this. And the common random numbers can also be very easy to apply because I don't need to have common random numbers globally because every time is only compare a pair of alternatives in a local process. All I need to do is to make sure that these 2 alternatives using common random numbers. So it's very easy to coordinate them. So it has a lot of benefit. It has a lot of benefit here. And then we'll care about, what is the total sample size of this knockout tournament procedure here. There are essentially 2 competing forces here to determine the first one is the best alternative now only need to survive, log base 2K games instead of K minus 1. So therefore, so in the past, sort of in the classical procedures, the best has to survive all k-1 comparisons. So the amount of error you are allowed to make, you have to allocate it to all these k-1 comparisons. Now the comparison number becomes much smaller, so you can allocate it, each one with a higher amount of error. So if the allowed error is higher, then the sample size will become smaller. Very straightforward. So this will drive the sample size down. But however, there's another competing force will drive the sample size up, because the sample size of the previous game cannot be reused. You have to throw them away. So that will increase the sample size. But the good news about that is that, so on average, each alternative only need to play less than 2 games. So in the worst case, the sample size is double. So, but there's another very interesting technical issue here, is how to best allocate the error alpha to all rounds of games. So in the classical game, the alternative, the best alternative has to survive all k-1 comparisons, because we don't have any information about other k-1 alternatives. So therefore, we allocate the error equally to all the pairs. So alpha divided by k-1. But here is very different, because in the first round, I have more games. Then in the second round, I only have half of the games. So therefore, if I allocate a bit more error in the first round, I'm going to save more samples because I have more games. So one very natural idea we allocate alpha over 2 to the first round, alpha over 4 to the second round, and so on and so forth. So if you think about the chance of making a mistake, the best alternative could be eliminated in the first round, in the second round, in the third round, and go on, so on and so forth. So if the first round is half over 2, the second round is half over alpha over 4, then you add up all the mistakes is strictly less than alpha. So by that, it's very easy to prove that this procedure will select the best alternatives, with a probability greater or equal to 1 alpha. Because the Kane procedure we used need an indifferent zone assumption. So therefore, this probability of correct selection guarantee is under this indifferent zone formulation. So in terms of statistical validity proof, it's very, very simple. So now we want to know, what is the sample size? So we consider a very simple case where all the variances are the same. So we apply the Kane procedure for all the games. So we compare, our worst case sample size with the worst case sample size of Kane. So for Kane, it's very easy to show that his worst case sample size is that one. So that's just corresponding to this maximum value of that triangular continuation region. So from here, we can see that for Kane, the total sample size grow linearly in the order of k log k. So essentially, it has to grow in the order of k log k. And it's very interesting to see that for this lockout tournament procedure I have just said, its worst case sample size is bounded by this one. So it's actually linear in k. It's a linear in k. So earlier we have shown that linear in k is a lower bound. So therefore, in this sense, this lockout tournament procedure is an optimum mean rate to achieve this lower bound. So I know it's maybe meaningless to compare, upper bound with upper bound. But still, nevertheless, we still can compare that. We compare this upper bound with that upper bound. We find that when k is above certain threshold, so the upper bound of our lockout tournament procedure is better than the upper bound of K procedure. So indicating that for large scale problems, k is higher, then our procedure may have better performance in terms of. So let's summarize the advantages we have seen from the KT procedure. first one is total sample size grow linearly in K, so it's sort of suitable for large scale ranking. The second is completely decentralized to different processes. Almost no coordination and communications are necessary among processes. So therefore, it's pretty suitable for parallel computing environments. And also the number of comparisons now is equal to the total sample size by K. So it's pretty trivial. The comparison is no longer higher order. So now it's become the same order as the simulation experiments. Number of simulation experiments become quite trivial. And moreover, because each game involves only 2 alternatives, so therefore you can use a localized common. So you don't have to do global coordinations. So next I will show you some numerical result. The first thing we did, we used the so-called slippage configuration, where all the inferior alternative has the same mean and the best alternative equal to delta, which is considered to be the most difficult problem to solve. So we can compare lockout tournament procedure with K in terms of the average sample per alternative. So if I look at the average alternative sample per alternative for K should be log K. In terms of growth rate is log K. In terms of local tournament, it's constant because it's already divided by K. So from here, so we increase the number of alternatives. So here is already log scale. So we see K is pretty much linear. So it's like the log K, while the lockout tournament procedure, like the theory dictated, it's more like a constant. So here, C equal to 2, meaning that, so when I do comparison in a local game, I just have 2 players play with each other. But however, for our procedure, we don't have to have 2 players play with each other. So we can have a small number of them play with each other. So here, if we use C equal to 5, so we find that the sample size requirement will be smaller. But the basic intuition here is that if you look at the lockout tournament procedure, so if the number of alternatives are higher, then its average sample size is smaller than K. So this is very much like our theory. We have tried another example. It's very similar sort of behavior here.
Jeff,
Yes.
could I ask a quick question? So I want to make sure I understand what C equal 5 means. Does that mean that you're applying Kn to a 5 system problem? Is that?
Yes.
Okay.
Yes, so it's like every local game, instead of 2 players play each other, so I'm going to have 5 players. So I'm going to apply a Kn on this small number for alternatives.
Okay, thanks.
So as we said, we want to solve a large-scale problem in parallel computing environment. So the previous experiments only show you the sample size. So we're going to use this 3-stage buffer allocation problem to test. So it's very interesting that in this ranking selection literature, simulation area, everybody used the 3-stage buffer allocation problem to test a large-scale problem. I don't think it's a good problem for ranking selection problem. But anyway, everybody use that. Let's just think about, let's ignore what the problem is about. But basically, you can select the different parameters, so you can have a different number of alternatives. So we have 3 different scenarios we consider. There are 3,000 alternatives, 57,000 alternatives, and over 1 million. We want to test them different parallel computing platforms. And so for the first 2 problems, well, the size still not too large. We use a local server which has 48 processors, and we use 2 different parallel computing platforms. One is Hadoop, the other one is Spark. Hadoop, as far as I understand, Hadoop is usually easier to program, but however, its coordination needs much more effort. So we compare our procedure with the GSP procedure of Eric Nee, Susan Hunt, Shane Henderson, this group of scholars from Cornell. And before the KT procedure, I think the GSP is the most efficient one. And GSP also uses sequential procedure, but use a divide and conquer scheme, trying to make the all pairwise comparison more efficient and in a better way to allocate the alternative into different processes. So we can look at the results here. So we can first we can look at Hadoop and Spark here. So Hadoop, because coordination requires more effort, work log time is much longer than if you use a Spark. And if you look at the total sample size, you find that KT, it's less than half of the sample size needed by GSP. And the GSP, as I said, did a lot of divide and conquer trying to reduce the comparison time. While in our case, it's very natural. Our comparison time is low. Our comparison time is still low. And if you look at the work log time in the under the Hadoop platform, so our work log time is less than 10% of GSP. In the Spark, where coordination is much easier, so our time is still lower than half of GSP. So this is for the problem with 3,000 alternatives, and we also look at the problem with 57,000 alternatives. We have pretty much the same sort of behavior here. So our the procedure KT, so the total sample size is about half of GSP, and also work log time is much smaller. And I think it's more interesting as we look at this problem, which has over 1 million alternatives. It cannot be solved by our local sort of server. So instead, we're going to use Google Cloud to solve. So we set up a cluster with 31 virtual machines on the Google Cloud, and then each virtual machine has 16 virtual CPU. So the total number of processes we have to allocate to different different jobs, actually 480 processes. And we run GSP and KT again on the Hadoop platform and the Spark. We also see very similar sort of behavior here, but I really like one performance measure here, last column. That's basically how much money you spend to solve the problem. Kind of like it. So you'll see that if it's under the Hadoop platform, we only need about 10% compared to GSP. If you use the Spark, we use about half. So that's sort of the numerical experiments we have on this lockout tournament procedure. So what I have presented so far is from a paper we have. It has already been accepted by OR, so it will be coming out pretty soon. So next, we're going to talk about some of the work we're working on now. So
Jeff, before you go on, could I just ask for a little on the previous experiments, just a little bit more insight. So GSP, while it's not tournament, it does divide things up into groups, right? And then compares results from groups. Where do you think the gain? What's your explanation of the gain that the knockout structure has versus the sort of divide and conquer of GSP? Where is the speed up gained?
I think I don't think lockout tournament in some sense is very similar to like a divide and conquer scheme, but it's actually not a divide and conquer scheme, because even after I divide a group of alternatives and put it in one processor, we're still doing this lockout structure. So it's really this sort of a tree structure that brings the benefit. It's not the divide and conquer.
Okay, thanks.
Can go on to talk about this extension. So the procedures that we have introduced so far are known as a fixed precision, because they attempt to select the best with a predetermined probability of correction. But in the ranking selection literature, there are also many fixed budget procedures, which basically attempt to allocate a fixed sampling budget N, capital N, to different alternatives in a way that they can maximize the probability of a correct selection. So there are various procedures have been developed. So like the OCBA family, it's an optimum computing budget allocation, or EVI, expected value of information, or knowledge gradient. So, but the basic idea, most of them are based on dynamic formulation. They want to dynamically allocate the sample so that they can maximize the terminating probability of correct selection. So that's the basic idea. Is many of them actually allocate one or one sample at a time. Sometimes they allocate one batch of observation at a time, in a way that they treat that as a dynamic program. In the end, to find alternative. They want to, in the end, they're going to select the alternative with a large sample. So essentially, if you look at all this procedure, what's behind it is they try to solve this optimization problem. So the sample allocation rule of this procedure designed to solve this optimization problem. Again, very much similar to Beckhofer's idea. So the best has to be better than all other alternatives. So now all I want to do is to allocate the sample in a way that I can solve the optimization problem. Well, this optimization problem is very difficult. And also, at the beginning of dynamic programming, I don't have any information. I have to collect the information to know something about that. So therefore, people typically use a approximation to solve the problem. Like the OCBA use a Bonferroni sort of bound of this objective function, and gradually use a sample to estimate and the variance in order to solve that. And there's very important result in the literature based on large deviation to drive everything into the limit and solve that. That's a so-called rate of optimum result given by Peter Glynn and Sandeep Juneja. So they use a large deviation approximation to solve the problem. Then they also expected value of information sort of procedure, like the one designed by Ilya Ryzov. They basically show that their procedure in the end will converge to the large deviation result of Glynn and Juneja. But the basic idea is everybody trying to solve this problem here and trying to approximate the optimum solution of this problem. So now what do we want to do? We don't want to solve that. So we want to study what is the theoretical performance of the optimum solution of this. So what we have done is say, suppose you know the optimum solution to that. Suppose n1 star until nk star is the optimum solution to the previous problem. Then we can prove a very interesting result. That means, given two conditions, that means the problem not become too simple. So that's a condition. What does the condition mean? So that means the highest, the best alternative, the worst alternative, their difference is an upper bound. So that means the difference doesn't go to infinity. Because if difference goes to infinity, the problem becomes too simple. Or for all alternatives, the variance is lower bounded. That means the variance cannot go to zero. Because if variance goes to zero, the problem becomes too simple. So these two conditions basically say when the problem do not become too simple, we can prove that if your total sample size grow in the order which is lower than k log k, then under this optimum solution, as k goes to infinity, the probability of correct selection goes to 0. So basically, this theorem suggests that for existing fixed budget procedure we have talked about just now, to ensure that their probability of correct selection does not decrease to 0 as the number of alternatives goes to infinity. So the total sample size should grow at least in the order of k log k. But in the previous fixed precision procedure we have talked about, we know that for KT procedure, the total sample size only need to grow linearly to ensure a non-zero correct selection. So that motivates us to think about, can we start, a very different sort of fixed budget ranking selection problem, not using the dynamic programming. So we tried this absolutely simple list of fixed budget lockout tournament procedure. So basically, suppose k equal to 2 to the power of L. So the procedure going to proceed round by round. You will select the best in L rounds. Then, so the number for alternative in each round is predetermined. It doesn't have to depend on, the mean and variance information. So all I need to do is to make sure that all L rounds, when I sum them up, let's say equal to n, the total budget. Then for each round, suppose I have m alternatives. I don't care what their mean or their variances. So what I'm going to do is I'm going to pair those alternatives, and I'm going to allocate the equal amount of observations for each alternative. Extremely simple lockout tournament structure. Then for each alternative in each round, they have the same amount of sample, and we're going to pair them. So again, so for each pair, we're going to advance the alternative with the larger sample, and so then we can go on. So very, very simple. And with this very simple fixed budget structure, local tournament structure, we are able to show that under the indifferent zone assumption, and as long as all the variants are upper bounded, all the variants are upper bounded, if we are going to allocate the total sample size in this way, you can prove that it's very easy to prove that sum of all the NR is actually less or equal to capital. If you allocate the sample size in this way, we're able to show that if the total sample size divided by k, that means on average, each alternative has number of observation greater or equal to eta. So eta has to be greater than 8. The constant that has to be greater than 8. So if that is true, then we can show that the probability of a correct selection of this procedure is bounded by this constant. So lower bounded by this constant. This constant is strictly greater than 0. And it does not including k in it. So what it shows that, so if I just use this very simple lockout tournament structure to design a fixed budget procedure, so the total sample size only need to grow linearly to ensure a non-zero correct selection. So this is a very simple sort of procedure, provide a very nice theoretical. But of course, in practice, if we're going to use this lockout tournament structure to solve the problem, we have to think about other way to design smarter procedures. So we have tried different ideas. Here, I just show you one of the most interesting ideas we have tried. So we know that in all the lockout tournament structure we have seen, no matter in tennis or in NCAA basketball games, and there's always, you're going to see all the players, right? So therefore, we use this seeding and pairing ideas, because in sports tournament, that helps the best player, best team to survive more games. So we're going to use the same thing. So, but different from sports games, which seed all the teams or all the players at the beginning, and the seed will not change. So what we do is we're going to seed at each round. So based on the sample mean information we have, based on the sample collected from previous round. So we're going to do the seeding here for each round, and we're going to pair all the alternatives use a very simple way. We're going to pair the highest seeding alternative with the lowest one, second highest with the second lowest one. Very straightforward, very common sort of seeding strategy in sports tournament, like in NCAA. So then I'm going to show you some experiments here. As I said, we're still working on this paper now, so I only have some preliminary results to show you. So this example, I have the total budget N equal to 200 times K. So I let K goes to infinity. You'll see that this optimum allocation scheme, probably correct selection will go down. For our very simple lockout tournament strategy, so it seems that the probability of correct selection will stay the same. Will stay the same. And I also tried the seeding idea. So now I make the problem more difficult. The total sample size equal to 80 times K. So we see without seeding this procedure, will still converge the probability of correct selection. In this case, appear to be non-zero, but it's much smaller. But just use the seeding idea, we see that probability of correct selection is almost 1. So that's sort of a very interesting idea here, and it shows very promising numerical results. But as I said, we are still working on this idea now. So to summarize what I have, so basically we have developed a lockout tournament procedures for both fixed precision and fixed budget ranking selection problems. And we show that the total sample sizes of this procedure rate are all optimum as K goes to infinity. And we also find that this procedure have pretty good performance in parallel computing environments. Okay, thank you. That's all I have.
Thank you very much, Jeff. We have some time for questions.
Sure.
Hi.
Hey, Ajit, it's good to see you. Hey, Ajit.
Yeah, good to see you. Can I ask a question?
Yeah,
Sure.
go ahead, Ajit.
Yeah, can you hear me?
Yes.
Yeah, okay. So I just have a question about your allocation of alpha among the different rounds. And you use the formula alpha divided by 2 to the power of R, right?
Yes.
Yeah. Okay. So is that in any way optimum? And secondly, I don't know if it exhausts all the alpha, because let's take, for example, we have 8 treatments, okay, 8 alternatives. And so in the first round, we give alpha by 2 among the four pairs. We got 8 alternatives. And the second round, now so R equals 2, we give alpha over 4. And the last round, when only 2 alternatives are left, we compare them at level alpha over 8. So alpha over 2 divided plus alpha over 4 plus alpha over 8, that's 7 over 8 alpha. So it seems to me that we are not exhausting all the alpha.
Right. Let me answer the 2 questions you have. First one, whether it's optimum, I don't really know. So we just basically tried this very simple strategy, and we find that it's a rate optimum. So that was sort of our goal here. So we should try that, but I guess whether it's optimum will perhaps depend on mean and variance information. So we find that this simple strategy would achieve this lower bound, so rate. So the second thing, definitely, if we're going to use this way to allocate the alpha will not be exhausted. So what we can do is that in the last round, we can double the amount of error. So that will be sum up to 1. But in terms of theoretical result, basically, we just show, because we're a lot of cases we care about when K goes to infinity. So when K goes to infinity, then the number of rounds will also go to infinity. So this single strategy will make sure that the total error is less or equal to alpha.
Yeah. Anyway, the question of optimality is not easy to address, but it seems to me that the fact that you are not exhausting all the alpha, that means it is definitely less than optimum.
Yeah. Yes.
So I think you can kind of easily adjust your allocation per round so that at least over the rounds, or no, so in the case of 8 treatments, you got 3 rounds. You can easily, you exhaust all the alpha. That alpha 1 plus alpha 2 plus alpha 3, if you call it like that, they will sum to alpha.
Yeah.
Okay, that's my question. Thank you.
Thank you, Ajay.
And a very nice idea, I think, brilliant idea, and you utilized it very well. So compliments to you.
Thank you. Thank you, Ajay. Yeah.
Jeff, I have a computational question. Can you hear me? Yeah.
Yes, I can hear.
So when you showed the utilization, it only went up to like 50, 60%, right?
Right.
And is that so? Okay. So Hadoop clearly didn't do so well, probably with communication or setup or whatever. For Spark, is that the problem because you have so much communication? That's the best case, even. But when you went to really large ones, it was
right. Sure. Really large ones. It's about half.
Right. And is that? I mean, so each pair terminates at a certain, not at the same time, right? There's this criterion, and then you're done early with some of them, right? So is that because of a synchronization issue? Because you wait, like some runs are done earlier than others? Is that because the processes are then idle? So, or is that so? And is that
yeah?
Is that a fundamental issue? Or can you just change it by the implementation?
So when you compare a pair of alternatives, they will always stop at the same time. So what happened is that because we divide the alternative into groups, and different groups, they may stop at a different time. So that is a place where if we have multiple processes, you may have to wait. So there's a amount of coordination here. It's like if I use the French Open as one example, so I have four courts for the players to play. So if 3 courts finish early, but the one last one finished very late, so then you have some sort of waiting here. Another thing is that in the end, you have 48 processes. Then in the end, we have, let's say, 48 players. Then we run into the problem that we have sort of fewer players than the number of processes. So we have to do some special sort of treatment there to utilize the processes. So what we have discovered is that towards the end, this tail will actually we spend a lot of effort in the tail. So one way to speed that up, basically, if you have a number of alternatives smaller than the number of processes, just let them run until the end. So that turned out to be a better way.
I see. I mean, if you have, to talk about your analogy with the chords, if you have 1 million players and you have 48 chords, they were just queuing up in lines behind the chords, right? So there's no reason why the chords would have to be empty at the first stage because you have so many pairs having to play. So the beginning, you can probably, if you just have queues or whatever, even that out. But I understand that the end, that could, you can't really fix that well. Yeah.
Right.
Okay. Yeah, thanks.
Thank you.
Other questions?
Yeah, I have a question if that's all right. I think, so this is kind of a hypothetical. Maybe this question is best described as sort of dynamic seeding or dynamically generating the bracket. So I understand that from each round, for various reasons, you can't reuse the old observations. But I wonder, I'm not sure how this would affect the computational structure or theoretical guarantees, but just from a sample size efficiency standpoint, I wonder if it makes sense to sort of retain all of the observations for the purposes of ordering. And then after each round, recompute the seeds, and then
right. Yeah. So maybe I didn't explain clearly that what you said is exactly what we did. So we can actually use the information collected from previous rounds to at the beginning of each new round, we're going to rank them. So we're going to have a new seed. Yeah, so it's actually a pretty good way. So we even go on and did this. So at the beginning, so I'm going to allocate a small amount of sample to every alternative without doing any elimination. Just compute their sample. So once I have the sample mean, I can start my elimination by I have a ranking here. So essentially, I have a seeding plan here.
Oh, I see. And so, but in terms of does the seeding change after every elimination, for example, or is it sort of
so it changes every round.
Okay.
Because based on the new information. The nice thing about this, because even though we reuse the previous information, and the way we prove the probability of a correct selection is essentially is rounds by rounds. I added them up. So essentially using Bonferroni inequality. So therefore, this dependence will not come into play. Yeah.
Other questions?
Hi, Professor. So I had a question, like I have heard about ranking and selection in context of online learning. So I wanted to ask if these two ideas are related.
Contextual learning. So this is I would say ranking and selection and multi-arm banded problems are very much related. So if you look at the history of these two branches, they pretty much started around the same time by the same people. And then one of them ranking and selection problem, look at the offline problem. So you have the, you solve the problem, you find the best, then we're going to implement the best. Then you have the multi-arm banded problem, which is to look at the online problem. So they're going to look at the entire life cycle of these experiments. I try to minimize the regret. So I would really see it's like very much similar problem. But of course, later on ranking and selection problem I studied many in the field of statistics and also in the OR field. Then the multi-arm banded many studied in the computer science field. But I think there are quite a lot we can learn from each other. But when you talk about the contextual learning, so then it becomes different. So now you have some contextual information there. So those classical ranking selection problem or classical multi-arm band problem, try to pick up best from K alternatives. But when you have contextual information now, what to consider to be the best depends on contextual information. The problem become a lot more difficult.
Okay. Thank you.
Other questions for Jeff?
I have a question for you, Jeff. Thanks for the talk here today. At the end, when you were talking about fixed budget knockout tournament, it made me think of median elimination procedures from multi-arm bandits, which is more of a fixed precision procedure, but at each stage it eliminates the bottom half of the systems based on their sample means. And the knockout tournament is also eliminating half of the players at each stage. So I was wondering there if I followed correctly for the fixed budget knockout tournament, it's not running KN for individual games, but rather all the surviving systems are simulated for the same amount. They're paired up and you look at their sample means paired. Is there an advantage to pairing them versus just dropping the bottom half in terms of giving the same PCS kind of, if that's what you're going for in a fixed budget setting?
Right. I mean, first thing I want to say this median elimination sort of idea. So when we had this work, we didn't know that, but then so there's really certain amount of similarities here. Compare the lockout tournament idea with the elimination, like what you said. So if we always have a pair of alternatives comparing with with each other. So every round we are actually eliminate half of the alternatives. So we started looking at this problem from a more sort of a parallel computing environment. So that's why I think in our case, because we sort of divide them into groups, into different processes, it's very natural for parallel computing environments. But if you do median elimination, then at the end of each round, you have to sort all of them. So you require a tremendous amount of effort there to first you sort and also coordinate all the process, all the rounds. So there's a difference over there. And the question you have just said for fixed budget procedure, because we will also think about the parallel sort of environments, but would you say that certainly makes sense if because I'm allocating the equal amount of sample to all of them, I could certainly just drop the second half. Yeah, I think it makes sense. It makes sense. So yeah, I don't know. I have to run some experiments to see what's going on.
Yeah, my sense is in that fixed budget case, if you look, the paired tournament is not necessarily taking the top half of the systems means, but rather is doing some pairing and is getting sort of a scrambled ordering of the surviving systems, whereas a median would just be cutting and surviving.
Yeah, that seems makes sense because that also eliminated the necessity of speeding, right?
I guess it would there, yeah.
Right. But what I find interesting in this sort of idea is that, so, I mean, to me, I'm just curious, whether we'll be able to sort of embed this sort of idea into dynamic programming. Because currently, I think the objective dynamic programming trying to minimize the probability, the alternative K has a higher sample mean. That's perhaps a wrong objective, as we have shown. But there got to be some other objective to fit into the dynamic programming structure. Yeah, that's something I have been thinking, but I haven't got a clue how to solve that.
That's a good point. Thank you.
Thank you.
So Jeff, we know it's after midnight for you, so we won't keep you too much longer. If I could just pick up on one thing related to David's question. This is in the fixed budget case. So the complaint I could imagine if I was a referee on this is that if you look at things like knowledge gradient or other kinds of things, when you do stop, you can make some statement like about the posterior PCS or something like that. So at least in the formal procedures, even though I'm exhausting a budget, at the end, I have some sort of statement about what it is that I've gotten. It seems like that's going to be, at least in the version of the procedure you described, while I can believe it's loads more effective in actuality, do you conceive of being able to say something at the end about the goodness of what you've got?
That's a good question. Well, there's a theoretical lower bound, right? So that's something we can estimate. Beyond that, I don't know. That's a very good question. It's at the end of the selection, what sort of inference can I do? Right. I think that's a very good question. That's something we should look at. So the way we look at it, basically say, you have a very large scale problem, and if you just have limited budget, so what is the best way to sort of allocate?
Right.
So, yeah, but it will be pretty difficult in the sense that because we have an elimination, and again, so it seems that elimination is absolutely necessary.
Mhm.
Because otherwise you always pick up the alternative with the highest mean, right? Highest sample mean. That seems, in when k goes to infinity, that's not a good idea. So, but with elimination, so how we're going to make it,
Yeah.
especially with many rounds, I don't know, but that's a question we can certainly look into.
But I can certainly believe that in actuality, it's tremendously effective. And, exactly as you showed, that, if you knew the answer and could evaluate it, you would find that you're doing really, really well. Okay.
Yeah, but that's a pretty difficult problem to analyze. I
Yeah.
can imagine. Yeah.
Yeah. Okay. Well, so maybe we'll say thank you to Jeff again for a very nice talk.
Thank you. Thank you for having me.
And Dave, I don't know if you got a chance, Dave Morton, to just say hi to Jeff today or not.
I didn't, and I know it's late, but I was just going to stick on for a couple minutes here.
Yeah.
Hey, hi, Dave.
Hi. So thanks for great talk. It was really interesting.
Thank you. Thank you for having me here. Yeah, it's great. I mean, I've just noticed that since I graduated, I've visited the department many times, but never give a seminar.
Uh-huh.
Yeah, this is the first seminar I gave. I feel very happy. Yeah.
Very good, good. So one question I had was, right, so and maybe it's tied into the KN procedure or what, the pairwise bit, but is pairwise somehow is that the right thing to do or the natural thing to do, or could I have a competition between 3 and have like a log-based 3?
Yeah, it's a very good question. As we've shown in this graph, I see that means how many players I have in a competition in a game.
I see. That's the C that Barry asked about.
C equal to 2 and C equal to 5. So practically, if you think about C equal to 2, so one of the problems is that you often have 2 alternatives which are very similar to each other, but both of them are not good. But because the KN has to select one out of those 2, you end up spending quite a lot of effort to tell which one is better. But even you find which one is better, then in the next round, maybe eliminate quite. So that's the thing we have discovered. So that's why we find that if we just make the group size slightly bigger, so then that problem will become a lot better. So that's why in the numerical experiments, the numerical experiment we reported here, we didn't use C equal to 2. So we used C with some larger number. Yeah.
But Dave, a different take on that is, even at that, you're still with a group of 5 doing pairwise comparisons within that. And Dave Goldsman's holy grail problem for years has been, can I design a procedure that in some sense is comparing 3 simultaneously without pairing them, so I'm not having to break up the error into the individual pairs? And that problem seems to be really, really hard.
I see.
Yeah. I thought about that problem. That's more like a holy grail. But however, I now have a different thoughts on that. So that tells us there's a conservativeness coming from the Bonferroni inequality, right? Because we always break it into pairs. What I've learned from multi-arm bandit literature, I look at the UCB. So in their derivation, they use Bonferroni inequality many times, and yet they still achieve the sort of lower bound in terms of rate. So I suspect the Bonferroni inequality here may affect the constant in front of the rate, but perhaps not going to affect the rate. So when the K become higher, the Bonferroni inequality is not all that bad. That's what I can say.
I see.
All right. Well, Jeff, thanks a lot. Say hi to your family for me. And
I will do.
it'll be interesting to see what Emily finally decides, although it seems like it's pretty clear on where she's
Pretty
going.
clear. Yeah,
Yeah.
she's going to Cornell.
Yeah.
Yeah.
She's going to accept Cornell. Oh, okay.
Yes.
Okay.
Yes.
All right. Very good. Okay.
Okay. Thank
Great
you.
to see
Good
you.
night. Thanks. Bye.
Bye.